How you want to manage that, that's up to you. But you're going to want to practice the math. So, energy expenditure is calories. So, let me give you a definition of calorie. Calorie is actually a measurement of heat. So specifically, 1 calorie is the amount of heat required to raise 1 gram of water 1 degree Celsius. 1 calorie is the amount of heat required to raise 1 gram of water 1 degree Celsius. So when we typically use the word calorie, like a dietary calorie, like if we were to say this apple has 100 calories, those dietary calories are actually 1,000 calories by this definition. So we actually refer to them as kilocalories. So that's why whenever I write calories, I will write it as kcal. I pronounce it calories, but I'll write it as kilocalories. But it's a unit of heat, okay? So calories will be expressed either in total calories or in calories per minute. So it could be like, during my run, I burn 8 calories every minute, and I ran for 20 minutes. And you figure out how many total calories you burned. What would you do? What would you type into your calculator? 8 times 20. So what do you get? And then this is total calories because the minutes would cancel out. Okay? So calories can be expressed either way. Calories per minute, or if you know how many minutes you're doing it for, you can figure out total calories. Okay? So, to measure this, one way to do it is through direct calorimetry. So, direct calorimetry, we're directly measuring calories, we're directly measuring heat production in your body. So, you know, when you're exercising, you give off heat. Your body's producing heat. So, direct calorimetry, to do that, we have to build a special room that has pipes in the walls, and there's water flowing through the pipes, and we know the temperature of the water. Then we put a person in there, and we have them run on a treadmill, for example. They're going to produce heat, right? The higher the intensity goes, the more heat they're producing. That heat that they're producing will increase the temperature of the water in the pipes. So we're measuring the temperature of the water to measure the heat that the body's producing. Okay? Couple problems with that. The treadmill is also going to produce heat. How do we distinguish between the heat from the person's body and the heat from the treadmill? Okay? Not all the heat that your body produces will be released. Some of it is held. Some of it might be absorbed by the walls. So a lot of limitations in this measurement. So instead we use indirect calorimetry. So it's indirect, meaning instead of directly measuring the heat, we're measuring something else that we know is related to the heat. And we measure that, and we can estimate the heat. Okay? So what we're measuring in indirect calorimetry is your oxygen consumption. And we write that as VO2. V stands for volume, O2 stands for oxygens. This is volume of oxygen. It's also going to be per minute. So volume of oxygen will be expressed either in liters per minute or in milliliters per kilogram of body weight per minute. Oxygen consumption. So VO2 I will pronounce as oxygen consumption, but I will write it as VO2. Okay? The dot on top of the V means per minute. So, as your exercise intensity increases, your heat production increases, your oxygen consumption also increases. So if we measure your oxygen consumption, we can use it to estimate your heat production or your energy expenditure. Okay, so that's what we're doing in indirect calorimetry. We're also measuring your carbon dioxide production, oxygen consumption, carbon dioxide production, but we'll talk about that a little bit more later. Okay, so measuring your oxygen consumption is easy. In the lab, we have a respirometer. You put on a mask and it's measuring how much oxygen you're consuming and how much carbon dioxide you're producing. It's hooked up to a computer and it tells you, gives you a number. Okay, it's pretty easy. In order to convert it into energy expenditure, the reason we're measuring oxygen consumption is so we can figure out your energy expenditure. So we know what the relationship is between oxygen consumption and energy expenditure. For every liter of oxygen you consume, you burn about 5 calories. For every liter of oxygen you consume, you burn about 5 calories. Another way to write this is 5 calories per liter. Do you understand that means the same thing? You consume 5 calories for every liter of oxygen you consume. Or you burn 5 calories for every liter of oxygen you consume. So, if you consume 2 liters of oxygen, how many calories will you burn? If you consume 3 liters of oxygen, how many calories will you consume? Okay, how are you doing that? You're multiplying the number of liters by 5. Okay, you can do that intuitively when the numbers are easy, but they're not always going to be easy. So let's say a person is consuming 2.13 liters of oxygen. Calculate energy expenditure. What are you going to do? What did you do when it was 2? You multiplied it by 5. If you have oxygen consumption in liters per minute, no matter how ugly the number is, if you have oxygen consumption in liters, you can multiply that by calories per liter to get the calories, because 5 calories per liter, the liters will cancel out. What's 5 times 2.13? 10.65. What's my unit? Calories. So if you consume 2.13 liters, you're going to burn 10.65 calories. What if a person consumes 1.21 liters of oxygen? Calculate energy expenditure.
6.05.
Okay, so you have to know, if I say calculate energy expenditure, what unit do I want? Either calories or calories per minute. You also have to know how to convert oxygen consumption into energy expenditure. So this is a number you need to memorize. Okay? This is called the caloric equivalent. This is our conversion factor that we use for converting oxygen consumption into energy expenditure. We have to have oxygen consumption in liters. To use this, we convert it into energy expenditure. Okay, this is an estimate for 5. It's not exactly 5. It ranges somewhere between like 4.6 and 5.1, depending on which substrates you're using. It's different for fat and carbohydrates. So in 446, you'll learn to calculate a specific caloric equivalent. For this class, we're just calling it a 5 to simplify things. Okay, but understand that that's going to change later. So to convert this into energy expenditure, we multiply by 5 calories per liter. What do we get?
6.05.
Say it again.
6.05.
6.05. And we're always going to go out 2 decimal places. And what's my unit on this? Okay. So oxygen consumption will never be given in just liters. It's always per minute, so it will be given in liters per minute. So what does that do? If I say someone is consuming 2.46 liters of oxygen per minute. Calculate energy expenditure.
12.3.
We're gonna multiply this by 5 calories per liter. What do we get? 12.3 exactly. Okay, can someone second that for me? Okay, what's the unit on this? Okay, liters cancel out, I'm left with calories per minute. Calories per minute. Which is still energy expenditure, right? Okay, let's do one more like that. Let's see someone is consuming 3.33 liters of oxygen per minute. Calculate energy expenditure. We multiply this by the caloric equivalent. Please tell me what you get. 16.65. Everybody agree? Unit? Calories per minute. Okay, so this is a pretty high intensity. If we exercise at this, do you understand this reflects an intensity? Right? As you increase your speed and grade on the treadmill or your resistance on the bike, you're working harder, you're going to consume more oxygen. So the amount of oxygen consumption reflects your intensity. The higher it is, the higher your intensity. So if you exercise at this intensity for 20 minutes, how many total calories will you burn? $333?
Yes.
Total calories in 20 minutes. Which means you could do that whole thing in one big long equation. So what if I said somebody is consuming 1.19 liters of oxygen per minute for 45 minutes. Calculate energy expenditure. So, how are we going to do that? 1.19 liters per minute. How do we convert that into energy expenditure? 5 calories per liter, but now we can also include the minutes. I'm going to say total energy expenditure. 45 minutes. So now you can type into your calculator 1.19 times 5 times 45.
267.75.
I'm sorry, say it again.
267.75.
266.75?
67.
67.75? Everybody agree? Now what's my unit?
In 45 minutes.
Calories. I'd like it to say in 45 minutes. Okay, liters cancel out, minutes cancel out, I'm just with calories. So this person is going to burn about 268 calories if they exercise at that intensity for 45 minutes. Yes?
When we draw the formula on the exam, does it matter the order of how it's placed or no?
It will not matter the order, but this is going to get more complex.
Yeah.
Because coming up, instead of giving you the oxygen consumption in liters, I'm going to give it to you in milliliters per kilogram per minute and ask you for energy expenditure. So now you've got to convert this into liters per minute and then do the whole thing. So I'm adding layers, okay? Do we understand the concept and do we understand the math? Those are two separate things. Okay. I have about half of the people nodding and half silent. So if you're lost, you're the one I need to speak up. Okay, because if you don't speak up, I'm going to move on as if you're with me. And I'm happy to repeat something or clarify something if you're lost. So please, please, please don't be afraid to speak up if something's confusing you, because there are going to be more layers added. Do you want another one like this, or are you ready to move on? Okay, do one more like this. Okay. 2.56 liters per minute for 32 minutes. Calculate total energy expenditure. See if you can do it on your own. Let me know when you get an answer.
409.6.
409?
0.6.
409.6.
In 32 minutes. Kcals in 32 minutes.
Okay. Somebody else let me know if you get that same answer or if you get something different. Same answer. Okay. So let me write it out for the people who are struggling. 2.56 liters per minute. And you're going to need to set it up in stoichiometry like this and show me how all the units cancel out. Okay, this is going to be using my caloric equivalent to convert it into calories per minute. And then I've got to multiply by 32 minutes. Minutes cancel out. Liters cancel out. I'm left with calories. 2.56 times 5 times 32 should give you 409.6. Any questions? Okay, now we're talking about oxygen consumption. You have a max oxygen consumption. Actually, we call it VO2 max, not max VO2, but either way. Do you have me for lab? We've talked about it in lab. If you don't have me for lab, have you talked about it in lab?
Briefly. Yeah.
Some of you a little bit? Okay, so your VO2 max or your max VO2 is the highest oxygen you can consume, highest amount of oxygen you can consume per minute, which is how we measure your aerobic fitness. So the highest amount of oxygen you can consume per minute is your VO2 max. That's how we measure your aerobic fitness. You also have a resting VO2. You're sitting in your chair right now. We can consider you resting. Are you consuming oxygen? Yes, you're not anywhere near your maximum oxygen consumption. Resting is the lowest oxygen consumption you can go to. Okay, you're not at your lowest right now because you probably ate something, you probably drank something, maybe with some caffeine, maybe you're stressed about class, maybe you're stressed about the math, which is going to change your oxygen consumption. So this is not, you're not where you are right now is not as low as it could go. Could go lower, like when you're sleeping is when it's as low as you can go. Okay, but that is your so your resting oxygen consumption is the lowest you can go. Max oxygen consumption is the highest you can go. Anything in between that, we call your submax. So that is like when you're exercising. If we're above your resting and below your max, you're at submax. Okay, so most of the time when we're calculating a VO2, it's going to be a submax VO2. Except in lab, we're calculating max VO2 to measure your aerobic fitness. Okay, so the higher your VO2 max, the more fit you are, more aerobically fit you are. Let me give you a critical thinking question. Here's person number one. Person number one has a VO2 max of 3.13 liters of oxygen per minute. Person number two has a VO2 max of 3.13 liters of oxygen per minute. Which person is more aerobically fit? Or are they the same? So what I just told you was, the higher their VO2 max is, the more aerobically fit they are, and then I gave them both the same VO2 max. But are they the same fitness? Something intuitively is telling you that's not right. So, in fact, they are not the same aerobic fitness. What does your intuition tell you? Which one is more fit, number 1 or number 2? Why? I heard mostly number 2. Why, Ricky?
Because number 2, the VO2 peak might be a little bit more, than number 1. So like the oxygen they consume when their intensity of exercise is greater, like they take in more oxygen than number 1. I'm assuming.
But we don't measure fitness by VO2 peak. Go ahead.
Their VO2 max in relation to their body weight.
Okay, explain. So what do you say about this person's body weight versus this person?
They're most likely.
They weigh more.
Yeah.
Okay, so can you explain your thought behind that? Why that makes them more fit? Or is it just your intuition, you can't explain it? Or were you saying it's number 1?
It's number 2, but it's just because like that formula is written on the board, so I'm assuming that it has something to do with their body weight.
Okay, go ahead.
So the body fat percentage,
Okay, how would that affect this?
if you lower your body fat percentage, the more, I don't know,
So which person are you saying has a lower body fat percentage?
person 2.
This person has a lower body fat percentage, therefore you think they're more aerobically fit? Okay, any other thoughts? Go ahead.
Number 2 trains at a higher intensity, but they maintain the same amount of VO2 or oxygen consumption as
Okay.
person 1.
Okay, go ahead.
More muscle mass would require more oxygen consumption.
Okay. So you're also saying it's number 2?
Yeah.
Ricky?
And then just agreeing with what was said, the lean muscle mass factor, that would perpetuate like a greater result.
Okay, so you have to answer, you have to vote. I already said they're not the same, so you gotta pick number 1 or number 2. Which one is more aerobically fit? Raise your hand if you think it's number 1. Raise your hand if you think it's number 2. So a lot of people are saying number 1, but nobody has argued for number 1. Everybody that's spoken up so far has said number 2. Go ahead.
I would say with number 2's muscular body composition, their VO2 max should technically be higher than 3.13, meaning comparatively with each body composition separately, 3.13, number 2 should be a little bit higher, and 1 is, I guess, average for the body type composition.
Okay, anybody else want to add to that? Anybody who was voting for number 1 who hasn't said anything yet? Go ahead.
I don't know if it's correct, but I know that aerobic exercises is more like the type 1 fibers, so the body composition would be like long endurance athletes, which is more what number 1 would look like than number 2.
Okay, but then how do you explain the numbers? Go ahead.
I'm thinking that because they have the same VO2 max, but number 2 has more muscle, that means number 1 is better able to supply their muscle with oxygen.
Yes. Yes, and what you said is also true. So, and we had some people earlier talking about number 2 saying because they have more muscle mass, they should be able to consume more oxygen than number 1. But they can't. They're consuming the same amount of oxygen as someone who has less muscle, which means the smaller person is consuming more oxygen per kilogram of body weight. So when you're comparing the 2 people, instead of looking at total oxygen consumption in liters per minute, we need to look at it relative to their body weight. How much oxygen are they consuming per kilogram of body weight, and then we can compare them. Okay, so although looking at it in these terms it looks like they're the same, this is not a fair way to compare them. Okay? Let me give you another example of that and add some terminology. So, let's say, that was great critical thinking by everybody though, I like that. Really good. Let's say you need to go buy a roll of paper towels. So you go to Vons, this roll costs $1, this roll costs $1. Which one's more expensive?
Smaller.
They're supposed to be the same size.
Oh.
Which one's more expensive? Or are they the same? Same. No matter which roll you choose, you have to give the cashier $1. But if you're a smart shopper, what else are you gonna look at? How many sheets it has. Okay? So this is Vaughn's brand. It has 100 sheets. This is Brawny. It has 50 sheets. Now which one is more expensive? Brawny, you're paying twice as much per sheet. Okay? Both of those are correct. It just matters which terms you're looking at it in. Okay? If we're looking at the total amount of money you're going to spend, where they're equal, that's called looking at it in absolute terms. How much total money are you spending? Whichever rule you pick, you're spending the same amount of money. They're exactly equal. Okay? If you're looking at it per sheet, that's relative. You're looking at it in relative terms. How much are you paying per sheet? So, these two units of oxygen consumption, liters per minute, is absolute oxygen consumption. Milliliters per kilogram per minute is relative oxygen consumption. So if we're comparing people, we need to do it in relative terms. Which means we need to be able to convert liters per minute into milliliters per kilogram per minute. So to do that, I need to give you their body weight. Any questions on the absolute versus relative concept? Okay, so let's say person number one weighs, let's do 130 pounds. We need to convert pounds to kilograms. How do we do that? What do we do with the 2.2? You're going to divide the pounds by 2.2 to convert it into kilograms. That's something you need to know. Tell me what you get. 59.09 kilograms. Can someone second that for me, please?
Yes.
Okay. So I'm going to take my 3.13 liters of oxygen per minute, and I'm going to convert it into milliliters of oxygen per kilogram per minute. So I need to convert liters to milliliters. How many milliliters are in a liter? Okay. Are the liters going to go on top or on bottom? I'm going to put the liters down here so they'll cancel out. So 1,000 milliliters goes up here. 1,000 milliliters per liter. Okay. Now I need to put the kilograms in the unit. In the unit I want, the kilogram is under the line. It's been divided. So the kilograms need to go down here. 59.09 kilograms. Okay. Here's what you type into your calculator. 3.13 times 1,000 divided by 59.09. If it's on top of the line, it gets multiplied. If it's below the line, it gets divided. Please tell me what you get.
52.97.
52.97?
Yes.
Okay, now what's my unit? Liters cancel out. I'm left with milliliters on top, kilograms, and minutes on the bottom. So you write it like this. Kilogram, milliliters over kilogram minutes. Okay, so person number one's relative VO2 max is 52.97 milliliters per kilogram per minute. Let's say person number two weighs 175 pounds. Calculate their relative oxygen consumption. Try to do it on your own, and then I will do it also. So you have to start by converting pounds into kilograms. Let me know what you get. 39.35. Anybody else get that? Okay, anybody get something different? Or you're stuck and you don't have a number? Please don't be afraid to speak up. Okay, so person number 2's relative VO2 max is 39.35 milliliters of oxygen per kilogram of body weight per minute. Now we can compare them. Which person is more aerobically fit? Person number 1 is an obviously higher number. They're more efficient. They can consume more oxygen per kilogram of body weight. Questions on the concept or the math? So you need to be able to convert liters per minute into milliliters per kilogram per minute. We also need to go the other way. Because if I give you, VO2 max is usually in milliliters per kilogram per minute. So if I give you a VO2 in relative terms and then ask you for energy expenditure, which is what we were doing before this, to multiply it by the 5 calories per liter to turn it into energy expenditure, you need it in liters. So now you have to convert from milliliters per kilogram per minute into liters to do energy expenditure. So you've got to be able to go both ways. Okay, so we're going to practice that next. I'm going to erase this. Is that okay? Oh, before I do that, let me give you average numbers for VO2 max. Just to give you some context here. If you have me for lab, we did this in lab. So, this is VO2 max. So, an average untrained woman, young woman, might have a VO2 max of about 40 mLs per kg per minute. An average trained young woman might have a VO2 max of about 50 mLs per kg per minute. An average untrained young male might have a VO2 max of about 50 mLs per kg per minute. And an average trained young male might have a VO2 max of about 60 mLs per kg per minute. So notice that the average male has a higher VO2 max than the average female. That's because the average male has larger lungs, so they can move more oxygen in and out. They have a higher blood volume, so they can deliver more oxygen, and they have larger muscle mass, so they can consume more oxygen. Is it possible for a woman to have a higher VO2 max than a man? Absolutely, but on average, they do not. And also that it goes up with training. Okay? Important to have an idea of what these numbers mean, so that when we're talking about it, you understand them in context. But also, when you're doing your calculations, if you calculate someone's VO2 max and it ends up being 16.4 mLs per kg per minute, you did something wrong. If somebody has a VO2 max of 16.4, they won't be able to get out of bed, because walking around requires more oxygen than that. Okay, if you calculate a VO2 max of 194, you did something wrong. It's not possible. I think the highest ever recorded was something like 93 or 94. Okay, so it's going to help you with your calculations to know that you're in the right area. Notice when I was giving it to you in liters, it was like 1, 2, 3 liters. Those are normal numbers for liters. These are normal numbers for milliliters. Okay? I'm going to erase this. Erase this.
I have a question. So are you saying that they're gonna be in between those numbers no matter what? Like there's no lower, no higher?
No, this is average.
Just average?
Yeah. So an unfit female might have a VO2 max in her 30s. A very fit female on the cross country team probably has a VO2 max in her 60s. This is average. Yeah. And you should be testing your VO2 max in your lab. We've already done it 3 different ways in my lab. Go ahead.
When you say trained and untrained, is that like trained specifically for aerobic activity?
Yes, yes. Strength training will not typically affect your VO2 max. Okay, so now let's say I'm giving you a VO2, but this time I'm going to give it to you in milliliters. And we're going to calculate energy expenditure, okay? I'm not giving you a VO2 max. I'm giving you a VO2 submax. Because if I'm going to have you going for 20, 30, 40 minutes, I guarantee you're not doing it at your max. Your VO2 max is not intensity you can sustain. It's an intensity you can barely touch. So you'll be working at a percentage of that, which we're going to do next week. So the VO2s are not going to be in the 40s and 50s that I give you. Maybe the 40s for men. Okay, so the VO2, so I'm not writing max. So this is not a VO2 max, it's a VO2 submax. So I'm just writing VO2. Let's do 28 milliliters per kilogram per minute. I have to give you the weight in order to convert it to liters. So let's say this person weighs 165 pounds. I want you to calculate energy expenditure if they exercise at this intensity for 30 minutes. Okay, we haven't converted in this direction before, so let's do it together. 28 milliliters over kilogram minutes. We need to convert this into liters per minute. How many milliliters are in a liter? Okay, now are the milliliters going on top or on bottom? We need the milliliters down here this time because we want them to cross out. 1,000 milliliters per liter, the liter goes on top. Okay, now I'm trying to get rid of the kilograms, so the kilogram's going to go on top or on bottom. Okay, so everything's opposite when we're going in this direction. Same process, opposite direction. So we need to convert pounds to kilograms. How do we do that? Okay. I got exactly 75. Is that what you got?
Yes.
And you just put that over 1. Okay, now in your calculator, you can put 28 divided by 1,000 times 75. You could also do 28 times 75 divided by 1,000. With multiplication and division, the order does not matter. You'll get the same answer. Tell me what you get. 2.1. Whoops. Okay. Kilograms cancel out. Milliliters cancel out. I'm left with liters per minute. Everybody good with that? That's a reasonable number. It's the range we've been in. Go ahead.
In this case, would you also want us to specify for 30 minutes?
Well, we haven't included that yet.
Oh, okay.
Right now, we're just at
yes.
2.1 liters per minute. we haven't gotten to energy expenditure yet. Okay, we just need it in liters per minute so that we can convert to energy expenditure. Now, how do I convert this to energy expenditure? Multiply by 5. What's the unit on it? Per liter. What did we call this number? Caloric equivalent. You need to know that number. That is how we convert from oxygen consumption to energy expenditure. Can we add the minutes on here, or do you want to do that separately? You okay with me just putting it on the end of this?
Yeah.
Times 30 minutes. Okay, so now we're doing 2.1 times 5 times 30. What'd you get?
315.
Okay, what's the unit? Calories in 30 minutes. Okay, we're gonna do another one exactly like this, but we're gonna do this all in one big long equation. Same steps. The first step is converting, to liters per minute. Next step is converting to energy expenditure, and then going all the way to total. Go ahead.
Do you always want us to convert pounds to kilograms before just adding an additional thing into the?
If you want to do it here, then that's fine. As long as you're showing me your work, that's fine. I like to do it before. Okay, I'm gonna erase this and give you a new one. Everybody good? And I'm gonna put it all in one big long equation. Actually, putting it in that calculation will be more accurate than the way I'm doing it, because you will be rounding the kilograms. And I'm rounding the kilograms. Okay. Different VO2, I'm gonna give you a different weight, I'm gonna give you a different time. So, I'm gonna say 39 mLs per kg per minute. How much do you want the person to weigh? 155 pounds. How long do you want them to exercise for?
25.
Did you say 25 or 45?
25.
Okay. Person is exercising at 39 mLs per kg per minute. For 25 minutes, they weigh 155 pounds. Calculate energy expenditure. I'm gonna write this all out in one big long equation. You're welcome to do it in steps if you want, but don't round when you stop at the end of a step. You gotta keep the whole number, or you're gonna end up too far off from mine. So I'm gonna write it on the board. You're welcome to follow along. If you feel comfortable enough, do it on your own. I'm gonna set up my units first. That's true. I hope you're not following along with me. What did you get?
44 calories in 25 minutes.
Okay, milliliters cancel out. Liters cancel out. Calories don't cancel out. Minutes cancel out. Kilograms cancel out. I'm left with calories. It's going to be calories in 25 minutes. Okay, I put the brackets here to show you the 3 different steps, but it's better if you don't stop. So you can do all the multiplication and then divide it by 1,000, or you can go to the right. Go ahead.
Do you always want us to do a specific amount of decimal places?
2 decimal places. Yes,
Do you want us to round up?
I want you to round correctly to 2 decimal places. Go ahead.
So for this, if you were to give us this on the test, would we be able to do it kind of like the way we understand it, or would it have to be the whole equation at once?
You need to show your work. You need to show me how the units cancel out.
For sure, but can we like kind of separate the two?
Yes.
Okay.
Yeah, you will be doing these on the test and you will have to show your work. And you will have a calculator. Okay, so we do another one? Let's say they're working at 24.36. They weigh 189 pounds and they're exercising for 48 minutes. I'll give you a minute, try to do it on your own. Let me know when you get an answer.
502.26 calories in 48 minutes.
Anybody else get that?
I got 2.
You got what?
I got 2, 1.
502.21, that's fine. Do you see anything you did different?
I think I just put all the numbers like together, but no, that
Yeah,
makes sense.
that's fine. There's some leeway there. Questions on the concept or the math? Okay, now, what if I told you that this person's VO2 max is 51 milliliters per kilogram per minute. What percent of their VO2 max are they at? Do you know how to figure that out? They're at 24.36 and their max is 51. What math are you doing? What are you typing into your calculator?
24.36 divided by 51.
Okay, so it's just like how I calculate your percentage on the test. I do your score divided by the total points possible to get your percentage, right? So that's submax divided by max. That's how you do percents. What you scored divided by the total points possible. So same with VO2. Submax, what they're exercising at, is 24.36 mLs per kg per minute. Max is 51 mLs kg per minute. As long as the units match, this works. Was 24.36 divided by 51? 0.477, which I'm going to make 0.478. How do we make that a percent? Multiply it by 100. This is for that 48% of their VO2 max. Questions on the math or the concept? You guys need to be able to work with percentages. Okay, let's do it the other way. Let's say the person is exercising at 35.33 mLs per kg per minute. And this is 80% of their VO2 max. What is VO2 max? What's the math here? And how do you know? Anyone know how to do this? Go ahead.
Would you convert the percentage back into its decimal?
0.8.
0.8.
And what do you do with
multiply
that?
that by the 35.33.
Okay, so if you do that, if you do 35.33 times 0.8, you're taking 80% of this.
Oh, and then.
And so you're gonna get a lower number, okay? So let's think about this conceptually. If they're at 35, we can just make it 35, make it easier. If they're at 35 mLs per kg per minute, and they're at 80% of their max, their VO2 max is higher than 35, right? So if you multiply this by 0.8, you're taking 80% of it. I didn't ask you what's 80% of 35. I asked you 35 is 80% of what? So what do I do? Go ahead.
Multiply by 100 and then divide by 80. Or,
Multiply by, that would actually work, I think. What's your logic behind that? Why are you multiplying it by
Or
100?
you could just like divide it by, but I'm setting up a ratio. Is how.
Okay, so, and I think what you're doing would work. But let me show you how it works in my brain. I do like a word problem. Do you understand if I say 35 is what percent, 35 is 80% of what? That's what we're trying to figure out. 35 is 80% of what? This is what I'm trying to figure out. So what do I need to do? I need to divide by 0.8. What do you get? 40.16? 44.16. What's the unit on this? Okay, so conceptually, if I'm working at an intensity that requires 35 milliliters of oxygen, and I'm at 80% of my max is 44. Alex,
I got a different number.
what did you get?
I got 43.75.
Because they didn't take
That's
off the
right.
0.33.
I did it with the 0.33. when you
Oh,
first
you
had
did
it.
35.33, okay. That's my bad for changing it. So 35 divided by 0.8, 43.75. Thank you for speaking up on that, because there probably had a lot of confused people. 43.75 if you use the 35 straight. Everybody good? Okay, so you need to be able to go back and forth. If I give you a submax and a max and ask you what percent they're working at, you should be able to answer that. If I give you a submax and what percent they're at, you should be able to figure out their VO2 max. You need to know whether you're multiplying or dividing by the percentage. If you're following along with the concept, if you don't know whether to multiply or divide by the percentage, if you were to multiply this by 0.8, you'll get a smaller number. If you're paying attention to what you're doing, you're going to notice that that number should not be smaller. And you're going to figure out, oh, I need to divide. If you're not paying attention, you're just going through steps, you're going to do it wrong. You've got to pay attention not just to the math, but if you understand the concept, it's going to help you figure out the math. Okay? Questions on this? Okay, so one of the concepts you need to grasp here as we move along with these calculations, and this is a tricky one to grasp and it's going to come up over and over again, is that any given intensity has a given oxygen requirement, which is why I'm assigning this person is working at 28 milliliters per kilogram per minute. That corresponds to a given intensity. Okay? Whether it's riding against resistance on a bike, running or walking on a treadmill up an incline. Okay? If I have two people side by side on a treadmill, they're both jogging at 6 miles per hour up a 3% incline, meaning the treadmill incline is on 3, it's a 3% incline. They're consuming the same amount of oxygen per kilogram per body weight. There's an oxygen requirement for that intensity that I can calculate, that we're going to calculate next week. Running 6 miles per hour to 3% incline has a given oxygen requirement. It's the same for everybody because it's per kilogram. Okay? If we convert it into total liters, the person who's heavier is consuming more total oxygen because they're carrying more weight. But per kilogram, same for both people. So, one person's struggling and one person is not. That has to do with how close to their max they are, right? If you're exercising at an intensity that requires 30 milliliters of oxygen per kilogram of body weight, and your max is 35, you're going to be struggling. If you're working at 30 and your max is 50, it's going to feel easy, okay? But that intensity has a given oxygen requirement, which is why I can assign this person is exercising at this oxygen consumption, because it's an intensity. So next week as we go into this, I'm going to show you how to figure out what speed and grade that is on the treadmill. In lab, we're doing it on a bike. And on a treadmill, actually, kind of. But I'm going to show you how to do it on a treadmill. So what you're going to be able to do, which is really cool, you should learn in lab how to estimate someone's VO2 max. In my lab, we did it out on the track, we did it on the step, we did it in the lab on the bike, we're going to do it in the lab on the treadmill next week. Estimating someone's VO2 max. Then if I was your trainer and I was going to program your cardiovascular training, let's say I want to put you at 80% of that. If I know what your VO2 max is, I calculate 85% of that, or whatever I said, 80%. That's going to give me your submax VO2. That's your target for your workout. I'm going to show you how to figure out what speed and grade that is on the treadmill. So I can give you your cardiovascular intensity that's exactly at the percentage of your VO2 max that I want, and I can calculate how many calories you're going to burn. Really cool stuff. Okay, so that's where we're headed with this. So there's going to be more math next week. So if you're struggling with this, please ask me, ask your peers, ask Eric. If you are good at math, this is probably fun and exciting for you. If you're if you don't like math, you're probably in a little bit of a panic right now. So if you're one of the people who's good at math, please help the people who are struggling, because I know this can get really frustrated, and this is a big point question on the test. All right, I'm done there. If you have questions, come on up.